So it's 9 o'clock on the West Coast, so good morning everyone, and good afternoon to those who are joining us from the East Coast. I'm Alex Boo, I'm the co-director of the BTK Center's Coordination Center. So we're wrapping up section 2 of our data science seminar, which, to remind you, has been an overview of data representation issues. We've covered a spectrum of different topics, starting with databases and data warehousing challenges through to issues related to data wrangling and exploration. And today we're going to hear about natural language processing, or NLP, from Dr. Noémie Elhadad of Columbia University. And for any of you who have had to deal with either unstructured clinical reports or other types of data, such as biomedical literature, you can already appreciate many of the issues of trying to get a computer to understand a textual document. NLP has been and continues to be an active area of research, particularly in regards to the biomedical space. So it's my pleasure to introduce Dr. Elhadad. She is an associate professor of biomedical informatics at Columbia, and as a data scientist, her efforts focus on the development of techniques to support clinicians, patients, and health researchers in the information workflows by automatically extracting and making accessible information from large clinical data sets. Two particular areas of interest in her research include computational approaches that infer models of health phenomena and that account for the specific biases seen in large health data sets, and the translation of these models into actionable knowledge and applications. Dr. Elhadad, we're delighted to have you with us this morning, and so without further ado, let's get started. The floor is yours.
Great, thank you, Alex. Hi, everyone. So I'm going to be talking to you about natural language processing and NLP in health in particular. And the way I think I'm going to structure this lecture is into four topics, and I'm going to spend most of my time on actually the first two topics. First one is to kind of give you an overview of the applications of natural language processing in health and healthcare. It's a very active field of research for core NLP methods, but you know, for the sake of this audience here, I think it's interesting to think about all the different ways in which texts and semi-structured text can be leveraged for advancing knowledge of biomedical sources or for helping clinicians in their daily care of patients. I'm then going to be spending quite some time on talking with you through some examples of why computing language is difficult. And I'll give you some examples both in the general and in the health domain too. And then I'll move on to some approaches in health natural language processing. There's been kind of a shift in computing approaches, and so it's interesting to kind of give an overview of those. And I'll conclude with the current developments in both domain generic NLP and health NLP research. So let me just start by saying something that might be obvious to you by now as human beings, which is that language is pervasive, right? Like us as women, when we talk to each other, we use language in written and non-written form. And the big revolution for us in the computing world is that there's more and more of such instances of written text available to us. And so this is an example of a de-identified clinical note. And the things to notice here, which are going to become a theme, is that it's English, you know, but it's not your typical English, right? So like there's a lot of abbreviations like HPI, which means history of present illness. And so if I were to read this first sentence, I would say 77-year-old male with history of hypertension, coronary artery disease, status post coronary artery bypass graft, 1988, meaning that happened in 1988. And so there, you can already kind of think about the challenges that we have here, right? That we are trying to maybe understand or extract some information from this type of text, and we have to somehow be able to encode or to reason about the fact that this note is about a male patient of that particular age at the time the note was written, and some procedures were given to the patient, like the cabbage, and we actually even have timing for these procedures, but there are also information about medications, symptoms, disorders, etc., etc. Another really important source of free text for people who do NLP is the literature, the scientific literature. And here, you know, there maybe the language is more structured, but it's still a very specific genre of text, right? And there are some things that we can leverage. We know that scientific articles have some structure to them, their backgrounds, methods, results, conclusions, etc. But they also have, you know, slightly complex sentences from a syntactic standpoint. And so if we want to be able to understand what type of information is being conveyed in these articles and do so at scale across many articles, then we need to be able to probably be able to parse these sentences accurately. Health news are becoming an important source of knowledge and trends in health and other domains as well. I'm sure you know, outside of health, there's all these interesting new things happening with fake news, for example. So how do we detect that something is a fake news? How do we detect that vitamin B12 is indeed correlated with higher cancer risk? You could think of the health news as a way to disseminate the information that's from the science, but with a very biased lens. And interestingly, from an hNLP standpoint, with yet a different style of language. And finally, another type of text that is of interest to natural language processing people is all the information that patients and health consumers are exchanging on the social web. So this is an example from a breast cancer, a publicly available breast cancer community. And I like this example because it kind of describes to us in a very clear fashion what some of our issues are going to be if we want to parse this type of text. And so this sounds like a very exciting. This is a thread. Chainsaw Z is the first person writing, and she's very happy. She said about someone else that she's glad you found Reggie, but I hope you dump him soon for the cuter one, Ned, or NED. And it sounds like it's not about cancer. It actually is about breast cancer. But what happens here is this common phenomenon in online communities where the community is coming up with their own abbreviations and nearly their own register of language. And so, in fact, Reggie is a regression of a tumor, and NED or NED is no evidence of disease. And so this is referring to the fact that someone has regression of her tumor and everyone is very happy. There's a lot of positive sentiment, which can be, by the way, identified automatically. But we also would love to be able to automatically identify that this person we're talking about had a regression in her tumor. So what are some of the applications that have been heavily using NLP? One that is a classic application and a very robust one by now, and still at the same time, for interesting reason, is becoming yet again a new research question, is automated coding of clinical notes. So the task here is I have a clinical notes, typically a discharge summary, and I have, on the other hand, I have a very large taxonomy of diagnosis codes, or ICD-9 codes, and I would like to be able to automatically say what are the most, say, 8 or 10 or 15 likely codes that can help me bill for a visit or that can help me represent what this note is about. So from a computing standpoint, the difficulty here is twofold, right? There's, on one hand, we have free text, and the second difficulty is that it's not a simple text categorization task because it's a multi-label classification, but the universe of labels is really, really wide. So ICD-9 codes, there's about 15,000 of them. And I'm sure you guys know we've actually in the United States now have moved to ICD-10 coding, where now we're talking about 65,000 plus codes. So again, from a computing standpoint, how do we train algorithms to recognize what are the most likely codes is an interesting question. A, a very classical question of NLP, where NLP has been used again in the clinical world, is the one of cohort detection. And I know you have had a lecture on information retrieval, so I'm not going to go too much into it, but it's an important one. By the way, I give example of articles that I think represent very well what the NLP challenges are and what the tasks or methods are, and so you're welcome to go and look at them. But they're just simple examples. There's actually quite a lot of research on each of those areas. And so here again, the interesting fact is that if we want to select a cohort, say, from the electronic health record, so if we want to identify in the electronic health record who are the patients who have a particular disease, in this example we're talking about peripheral arterial disease, then we know we could use some of the metadata that's available to us, but we also would probably want to use or leverage the clinical notes. And as a matter of fact, it turns out that when it comes to identifying cohorts, the NLP is often quite critical to identifying the right population. Clinical decision support is a traditional example of clinical informatics where, again, NLP would be useful. The idea here is to leverage the information from clinical notes within the logic of clinical decision support. So if we want to have an alert that looks at potentially dangerous drug-drug interactions at the time of prescription in the electronic health record, or if we want to make sure that we're not prescribing a drug when a patient has a specific allergy, this type of clinical decision support system will go and look at the structured information or the metadata available in the electronic health record. But again, there's no guarantee that there's some information, that all the information about the patient is encoded in the structured part of the EHR. And in fact, very often old allergies or old, things kind of fall through the cracks and are documented in the notes, but not in the structured part. And so NLP here again is extremely helpful. Another type of application is one of data exploration, and this comes from the fact that there's so much text available to clinicians, to health practitioners, to researchers, that we need to help and support them in just making sense of all the data that's available. So this is an example of a patient record summarization system that we have at Columbia University and is actually deployed and used by physicians. The idea here is that we're taking all of the notes longitudinally from, we have about 20 plus years worth of data for each of our patients. And we can, through natural language processing, identify what are the primary problems for that patient. And on top of it, have a visualization, an interactive visualization that allows the clinicians and EHR workers to explore and go through the timeline of a patient. This is another example of how NLP can be used for data exploration. This is in a slightly different genre of text. We're looking at autism spectrum disorder communities. So these are parents of children typically with who are on the ASD spectrum. And the question again is, there's a lot of discussions. How do I make sense of all of these discussions? Why would I want to do this? Maybe I'm a public health practitioner and I want to look into health communication issues, or maybe I want to learn about how parents are viewing certain treatments, or what is the awareness about particular disorders or symptoms for patients. And so here what we've done is we've created a set of named entity recognition system that can identify terms in posts. And so on the top right here, you see an example of a snippet from a post. And we then did so for all the posts in the community and built, again, a visualization to help with exploration on top that kind of builds a network of significantly occurring terms, pairs of terms. And so in this case, we are in, again, an autism community, and so stimming is a very specific to the language and the register and the domain of autism. But it's interesting to see in which context, basically, that type of term is being talked about. This is another example of data exploration from text that has been extremely successful in many different areas, actually, and this is one of topic modeling. And so this is taken from a paper that looked at all of the publications from Science Journal and is trying to make sense in a very unsupervised fashion about all the different topics or themes that have been talked about in the Science Journal over 100 plus years. So what is the challenge here? The challenge is that we do not know in advance. We're completely unsupervised, right? We do not know in advance. We're not making any hypotheses about what type of themes are being discussed in these articles. And we want a method that can allow us to identify what are the primary themes, and moreover, in the case of correlated topic models, like in this example, we want to know how these themes relate to each other. And so we can build this type, again, of visualization that tells us that, RNA, DNA, and that type of cluster of words here correspond to a significant topic or cluster, and moreover, it is quite related to, meaning it occurs or it correlates often with a topic about sequencing and DNA sequencing, and another one about proteins, for example. So the value here is that when you have a very, very large corpus given to you, for example, all of the articles published in a journal, and you're trying to extract to understand what are the primary topics discussed in that journal, like in this example. Or if you have a patient cohort with lots of electronic health record notes available to them, or if you have access to an online health community, for example, prior to detecting a particular phenomenon, maybe you want to just go and explore and understand what is being talked about. And so a lot of NLP methods rely on this type of topic modeling for data exploration. So another thing that you can do with this type of topic modeling is you can then look at how they change through time. So again, this is from the Science Journal article, where we have you can look at, these are examples of two different topics, and you can look at through time from the earliest years of publication of the Science Journal in 1880 up to 2000, what, for example, the mention of the term oxygen, and what was basically the interest maybe of oxygen about the journal. So keep in mind, we're not extracting information here, we're just identifying kind of salient terms that are representative of a corpus here. And again, it's not, it should not be interpreted as a literal representation of the corpus, but rather as a tool for data exploration. A more and more prevalent type of application has to come with surveillance from publicly available data sets. So this is a very active field of research. I'm putting here just two examples of papers, but there are many, many more, where we're looking at the authors are looking at public social media sources, so things like Twitter or Yelp, and trying to identify very specific occurrences of a condition. In this case, the authors and the Department of Health they work with are interested in identifying who has had foodborne illness after eating in a restaurant, so that they can go and maybe look at, go and investigate what's going on with that restaurant. So what are the challenges, again, here from an NLP standpoint? Well, on the top left, you see a Yelp review, and we want to be able to, knowing that we're looking at foodborne illness, we want to be able to go and extract that someone was sick, but not only just generally sick, but sick from eating. And that not only that, the symptoms of foodborne illness kind of happened after enough time that it would kind of, support the idea that foodborne illness came from that restaurant. And so it's a complex information extraction task. There's a bit of reasoning involved in here. Another challenge is that it's, especially if we're talking about Twitter, not all of the information is going to be nicely contained into a single text, and there is going to be maybe conversations and all sorts of like interesting linguistic phenomena such as co-references that are going to be needed to be taken care of to identify, for example, like in this example on the bottom right here, that this person indeed got sick and that was a particular location where the restaurant was the potential culprit for the foodborne illness. Researchers have been thinking about this idea of info surveillance quite a lot. This is HealthMap, which I encourage you to go and visit. This is work from Harvard and John Bronstein. And if you Google HealthMap, you'll find it right away. And it's a very nice interactive visualization of all the potential diseases that are being talked about on typically on the news, but they're incorporating other data sources as well in here. And so again, the same challenges come again, right? How do we identify that a particular disease is being talked about? And moreover, in this case, what is the location of where the patients are being notified about? So let me switch gear and continue with my summary of applications. This is going back to the clinical domain. We're interested in high throughput phenotyping. Why do we want to do high throughput phenotyping? We want to maybe be able to identify all conditions that are being talked about across a large cohort of patients, or maybe we want to do that same task as cohort identification, but instead of finding methods to do so very well for one disease at a time, maybe we want to do it for all diseases at once. And the reason I'm bringing up this example is mostly because the methods are very similar to the one of topic modeling. And they're interesting because they're taking into account not only the text, but also the other data structured information that we have in the electronic health record, such as laboratory tests, medications, and diagnosis codes. And so we can build NLP-based methods that kind of incorporate this additional information and bring better cues, basically, to identify what are the observations that enable us to decide that there is probably diabetes mellitus type 2 for a particular patient, for example. And so in this case, it's very much like topic modeling. It is an unsupervised method, and we can, moreover, kind of have a description of those typical conditions or phenotypes we're looking for. So, for example, here we have lupus, and we're finding kind of, again, very unsupervised fashion that anti-malarial are a medication class that actually makes sense for lupus. And for the non-clinicians out there, actually, that's correct. Anti-malarial are a way of treating lupus. Another type of application which is really, really big in healthcare, but is becoming really big also on more social media type of situations, is predictive analytics. So the question here is, can we use text, either text written about a patient, or in this case, in this example that I'm giving, text about that are written by individuals on Reddit, and can I predict whether they are likely, something is likely to happen, or they're likely to behave in a certain fashion. So this example, we are interested in mental health, and the authors are looking at subreddits that have people talking about their depression, and then they want to know, well, within 6 months, are they actually now moving on to another type of subreddit, which is more about suicide watch? And so the question here is, can I predict that someone is going to start ideating about suicide? And it turns out that there are very specific linguistic indicators that can help us predict who is going to be likely to move on from the mental health type of subreddits to the suicide watch type of subreddits. You can imagine there's a lot of interesting application that can come out of this work, but what's nice is that there's these cues that come from the syntax or from the type of words that are being used by people where we can actually predict what's going to happen in their behavior on an online community. Similarly, in the clinical world, we can again try to predict adverse outcomes. So here, this is an example of a predictive model that looks at progression of chronic kidney disease. And what's interesting here is that because we're in the clinical world, we want to be able to predict, but we also want to be able to interpret some of our learned rules. And so the type of methods that are used here are, again, unsupervised and are basically learning topics together with a kind of a temporal model, which is a Kalman filter in this case, but primarily for NLP purposes, the point is that we can learn topics of words that occur in clinical notes that are going to be more or less predictive or increasing risks for progression. Those are the orange/red topics in here, and the ones that are going to have a protective effect on patients. And so that's, again, useful because we can go further, generate hypotheses, and work further with clinicians on these questions. Okay, so I spent a lot of time on those applications, but I think it's useful, and again, there's many others. It's just useful, hopefully for you, and it's definitely helpful for me in my research, to think very widely about all the different type of texts as data sources and knowledge sources for the various type of tasks we want to do. But I want to now focus on, well, okay, so we know that there are lots of applications to natural language processing, but is it, why is it so hard? And more specifically, why can't I just use regular expressions, right? Like, so regular expression are just like models of what I expect a set of string or characters is going to look like, and it's going to help me search for a particular type of information on a large collection of text, for example. Why do I need more complex models of language? Well, the first problem is that language is ambiguous, and it's ambiguous at all linguistic levels. And for those interested in what I mean by linguistic levels, morphology, lexical levels, syntax, discourse, and pragmatics are all interesting levels to think about. And here are some of the examples that are the classic examples. So these examples are actually taken from the excellent course from Chris Manning at Stanford on natural language processing. And so here's one where there's definitely some syntactic ambiguity. Boy paralyzed after tumor fights back to gain black belt. Same for this other headline in the news: San Jose cops kill man with a wife. Kill man with knife. So where's the ambiguity here? Well, are we saying that who had the knife, basically? Are we saying that the cops had the knife and that's how they killed the man? Or are we saying that the cops killed a man who had a knife? And so that type of ambiguity is called PP attachment ambiguity. We don't know if we were to build a syntactic parse for that sentence, we don't know where we should attach that phrase with knife. Should we attach it to the head, to the noun phrase man, or should we attach it to the noun phrase San Jose cops? It's actually ambiguous. We do not know. We do know maybe as humans when we read it, because maybe there's some more likely scenario, but it's still ambiguous. There could be a scenario where the cops are killing the man with a knife. Sorry, that was ambiguous too. Are killing a man and they're using a knife to kill him. Some of our more clinical examples where ambiguity creeps in are very lexical for us in clinical texts. This is an actual example from a social history of a patient, and says patient sister in CA, mother breast CA. And so we have here a term a term which is CA, which happens to be an abbreviation. And those type of abbreviation are usually fairly ambiguous. In the first occurrence of CA, we mean California. In the second one, we mean cancer, and in particular, breast cancer. So how do we build a language model that can help us disambiguate between these cases? Moreover, there's other senses to this type of text, to this type of terms. For example, Ca also means calcium. So this lexical ambiguity is quite difficult. The other challenge with language is the one of variability, and again, it happens at all linguistic levels. Another way to think of it is that there's a high paraphrasing power in language, and it's a good thing actually, because we're not, as humans, we want to have ability to create new ways of saying new things, but also old things. There usually are some reasons to why you would say a sentence one way or another, but for the sake of computing, we want to be able to identify that maybe different forms of a term actually refer to the same concept, like on the example on the left, diabetes mellitus 2, diabetes T2DM, all of these three and many others. How can I build a model that recognizes that these guys are all talking about type 2 diabetes? And note that I put diabetes here as an example, and that's actually ambiguous. Are we talking about type 1 or type 2 diabetes? And so maybe there's some additional reasoning that would tell me that in my corpus, really, when I say diabetes, I mean type 2 diabetes, and I'm able to map or normalize all of these forms to a single concept. And so that's an example of variability on a lexical standpoint, but there's obviously a lot of variability in syntactically. John loves Mary, Mary is loved by John, the man who is named John loves Mary. All of these things mean the same thing, are paraphrases of each other, and are nevertheless conveyed with different syntactic structures. It's interesting to think further about the lexical ambiguity, and really go back to that question about diabetes. Is that, do we mean diabetes type 2 in general? So the context is really helpful in these things. And as a matter of fact, a lot of the computational methods are incorporating context to determine this type of language models. And so I thought I would show you a very simple visualization of what we mean by context. So here we have two online house communities. One is the same autism spectrum disorder discussion forum that I mentioned earlier, and the other one is a general parenting discussion forum. And we built a representation of all the terms that are being mentioned in those forums, and we do some normalization as much as we can. But we also then try to look for co-occurrences patterns, okay? And so two terms are going to have in this network an edge between them if they co-occur together more often than they do not. And so why am I putting these two networks here? Those are networks centered actually on a single node, on the node drug here. And similarly here on the ASD on your left, about the node drug, but as it is mentioned in the ASD, in the autism communities. And so what do we see? Well, it's two different, very, very different networks, right? And clearly you can say a lot about, even though they're exactly the same terms, they mean completely different things in different contexts, right? And so in the general parenting forum, drug is typically meant as an illicit or illegal drug, or a problematic drug like alcohol, marijuana, substance abuse. Pharmaceutical company is more about the pharma type of drug, and illicit. Those are the terms that are found as being statistically important related to drug. In the autism world, they mean, clearly they mean different types of drugs, and moreover, all of these drugs are very representative of the type of treatment that children on the spectrum are using. So again, from an NLP standpoint, the interest here is that even though there are terms that have exactly the same lexical information, they actually mean different things in different contexts. And so a lot of the methods that are being developed nowadays have to do with language modeling, with trying to represent or encode what is the meaning of a particular word through what type of words they occur or co-occur with. This is a similar example again. Language, same word on both sides means very, very different things in two types of context. In general parenting, when parents talk about language, they mean foul language or maybe bilingual language. Whereas in autism community, language is all about all of the potential symptoms related to autism, as well as potential therapies that have to do with helping with language difficulties. Okay, so the last one, the last challenge that I would focus on through very simple examples is the fact that language is vague. And another way to think about it is that maybe we need to reason about language. And like for the ambiguity and the variability challenges, it's present at all lexical levels. So there's three types of examples that I want to focus on. First one is one that we see quite a lot in the clinical world. This is two sentences, am I 3 weeks ago, am I 3 days ago? And so what's the question here? First of all, we need to recognize that MI means myocardial infarct in this case. That's fine. That's a lexical ambiguity or paraphrasing power question. But here I want to focus on that temporal expression here, which says 3 weeks ago, and here it says 3 days ago. If we want to actually reason over those information, and if we want to understand or represent the meaning of those occurrences, we need to understand that, first of all, this is a temporal representation, a temporal expression, and moreover, it is about that clinical event, which was a myocardial infarct. The last thing you'd want to do then is to say, well, okay, so if we were to establish a timeline of events of the patient, then I would use a time at which the note was written, and I would go 3 weeks in the past and put the myocardial infarct at that time, right? That would be the sensible thing to do automatically. Turns out that in the clinical world, that's not always correct. That's not always the right thing to do. I mean, it is the right thing to do, but it's more complex than that. And so what's going on? Well, we can actually find that when someone says, am I 3 days ago, in fact, the person said 3 days ago. They really meant that it happened 3 days ago. But when someone says, a clinician says 3 weeks ago, well, it could be 3 weeks ago, 21 days ago, but it could be 20 days ago or 19 days ago or something like that. And it sounds like it's not an important problem. It actually is quite an important problem for two reasons. One is that it's not always the case that this type of temporal information is available in the structured part of the electronic health record. We really want to rely on the notes because the notes are often talking about events that did not happen in a current institution or, you know, for various reasons. The second one is if we want to study temporal or time-related phenomena like adverse drug reactions or prediction of particular events, we really want to have the timeline down correctly. And so how do we know that when someone says 3 weeks ago, that really meant 21 days plus or minus 4 days, whereas when someone says 3 days ago, that really means 3 days ago. That's we need some reasoning here, or at least we need a way to encode this type of uncertainty about the language. Speaking of uncertainty, the next example is interesting as well, and that's something that happens actually very often in the clinical and in the health domain. So when I say Paul thinks that John loves Mary, there are a few things that are happening, right, from a linguistic standpoint. First is that there's a fact that says that John loves Mary, and now we, what can we say about that fact? Is it true? Is it untrue? What do we know exactly? We actually do not know whether that fact is true, but we know that a third person thinks that that fact is true. Similarly, this type of like pragmatic things creep up even in clinical NLP. When someone says, you know, patient denies smoking, we're not saying, you know, that's typically found as like patient does not smoke, but really when we think about it, it really means I do not know whether the patient smokes or not, but I'm going to encode it and I'm going to represent it by saying the patient denies it. It's something to think about when we do this type of information extraction and reasoning. In the health domain, that comes quite often. You can imagine if a patient says, you know, write a question online or searches for some symptom somewhere or writes to their peers, and they often would say, you know, I think this is happening, and there's a lot of uncertainty about all of this phenomenon that they're discussing. And so the last thing we would want to do as NLP practitioners would be to extract this information and just say, oh, look, it says John loves Mary, I'm going to just extract that fact as being true and ignore the other part of the sentence. So taking into account this uncertainty of language is very interesting. The final type of reasoning that's needed is coming, I think, is illustrated well by that tweet example where this person says that they just ate a bowl of Xanax for breakfast. It's true, it's a well-formed sentence, which, by the way, does not happen often on Twitter, so that's good. There's, you know, even the medication is well written in here, so there's no problem of like identifying that Xanax means Xanax. The question is, did this person actually eat a bowl of Xanax for breakfast? Probably not, right? And so is it sarcasm? Is it humor? Or did this person actually mean that they didn't eat a whole bowl of it, but maybe they ate a lot of Xanax? And maybe that want to be, you know, we would want to pay attention to that type of signal when doing monitoring of Twitter. We want to be able to build models that can recognize that there's something uncertain about this information. Okay, so approaches to health NLP. There are actually many different approaches out there, and I made kind of like an editorial choice in focusing on two types of methods. And I'll talk about a third one in the current developments, but keep in mind, again, I'm just giving you an overview, and I definitely suggest that if you're interested in the field of natural language processing in the health domain, there are wonderful classes online and tutorials, and I'm happy to, if you want to get in touch with me, to point you to some of them. So something that a task for which a lot of methods have been designed over time in clinical text and clinical NLP is one of information extraction. So the task is, if I have a sentence like this one, patient should come back if severe facial rash occurs. I want to be able to do some what's called named entity recognition, meaning that I recognize that facial rash is a disorder, is a type of problem that can happen to a patient. Not only that, it's a particular concept in a terminology. In this case, I'm showing you a concept in the UMLS, the Unified Medical Language System, which is a really large terminology. And maybe I'd like to extract other modifiers about these particular disorders. So in this case, maybe I would want to identify that severe is an important modifier here. And the if here is also, as you can imagine, quite important and is indicating that this is a conditional type of disorder. In other words, the patient actually does not have a facial rash, but the facial rash is discussed nevertheless in the context of this particular patient. So what other type of modifiers have been thought about? Many different ones. This is an example of a set of modifiers for disorders. We would want to normalize to a terminology. We would want to be able to identify negation, who the subject of that disorder is, who is the disorder attributed to, is another way to think about it. Is there uncertainty? Is there some sort of like progression or course mentioned about that disorder? What is the severity of the disorder? Is it conditional, like in the example earlier? or is it actually not a disorder? Like in this example, when we say the patient goes to the HIV clinic, really it says HIV, and HIV is a disorder, but HIV clinic is really the named entity recognition you would want to pay attention to. And if there is a particular body location that's affected by the disorder, like facial rash, facial is actually part of the important body location we would want to extract here. So there's been a lot of work in natural language processing to kind of define this type of schemas to figure out what it is that we want to extract in clinical text like this one. That's one type of work. And typically this is done through lots of annotations of text. And there's a whole field of research about how to do these annotations in a way that is correct, in a way that we can trust the type of annotation, that we found that the schemas are generic enough and can be applied to many different type of information extraction systems. And then, of course, we want to be able to build methods that are going to actually use this schema and then go on new type of text and identify those named entity being mentioned along with all of these modifiers. This is a really, really large field of research in clinical NLP. And so I'm giving here like literally 3 examples of like famous papers here on this domain, but there are many, many more. The example I'm giving here is from the CTEX system, which is actually open source, and you can try if you have any clinical texts. And the reason I like it is it kind of shows you all of the different part of the pipeline that the system goes through in order to do this named entity recognition. So there's a sentence here that says family of obesity, family history. FX is an abbreviation for family history of obesity, but no family history of coronary artery diseases. So the first question is, how do we tokenize? And this, I believe, in the text wrangling lecture, you guys had some discussion of that. We want to then identify the part of speech of all of those different sentences, the different words in the sentences, and maybe do what's called a shallow parsing, meaning we would identify not the whole syntactic structure of the sentence, but rather what are the primary noun phrases. So a noun phrase would be a term, a set of words that together refer to a noun, a head noun. And from there, we would then go and look for particular noun phrases that can be mapped to a terminology, like here. So obesity is found, and coronary artery disease is found, but also coronary artery and diseases. And all of those are potential named entities we would want to identify. Furthermore, the status for family history, for obesity is that it's a family history as opposed to the patient has obesity, and it's not negated. So nowadays, I think that the state-of-the-art type of named entity recognition system are using sequence labelers. And again, Sandra Harabed, you kind of mentioned it, and so I thought I would move on from them, but you can see what I mean here by sequence label, right? Like where I'm able to go through each of these terms, each of these words, and I'm slowly building up this particular term, coronary artery disease, by saying that this is the beginning of my entity, and I'm going to keep in my sequence of terms until I feel like it doesn't belong to the named entity anymore. I mean, you've heard me refer to terminologies quite a lot, and this is outside the scope of this lecture, but you realize, I hope, that we're relying heavily in this type of clinical task on lexicons or terminologies or ontologies. And one huge challenge is how do we ensure that the lexicon actually captures the language of the corpus under study? The UMLS is very large, but it's also quite specific, for example, to clinical and technical type of language. And so now when we are doing work in online health communities or on Twitter, we need to figure out ways to either augment or filter the UMLS. And NLP can help for this as well. Another type of approach that's been really helpful, and I've mentioned, is one of probabilistic topic model. And I would like to refer you for this of all the work of David Bly and all of the people who worked on this for the past 10 plus years. But the idea here is very different approach to clinical name density recognition, and is looking at, and is completely unsupervised, and is trying to find patterns of text, and in particular is trying to identify cluster of words that tend to co-occur quite often with each other, such that the documents that they appear on are considered to be a probabilistic mixture of those clusters or topics. And so you can, at the output of your topic modeling, or in this case, latent Dirichlet allocation, you can identify that all of these different words together are very likely to be part of that topic, and moreover, we could think of that topic as humans as being about genetics or evolution or disease in particular for that example. I have not talked at all about evaluation, but this is something that people think a lot about in health natural language processing. There's a lot of task-based evaluation. So when we do progression of disease, we think of a task-based evaluation as, did I predict who is going to progress accurately? And that's fine. But when you think about the core NLP methods, we do usually need gold standard annotations to do some sort of validation or internal validation or intrinsic evaluation of the core NLP methods. And again, it's a whole topic, so I'm not touching on it, but I'm mentioning it here. Okay, so I want to finish with the current developments in health NLP and NLP research. And this is a very exciting type of research that is happening for the past less than 5 years actually, and which is the advent of deep neural nets in the world of linguistics. And so I felt like I couldn't really point to you to very specific papers, but if you are interested in the context of deep learning and natural language processing, Richard Sauter at Stanford has an excellent class, and all the material is given online, and so I suggest that you go and either read or even try to do the homework. But I thought that basically there's like 4 areas that are very interesting, I think, from an NLP standpoint as far as like new areas of work. One is a better or improved language models. We know already that we need good contextual representation of what words are, and now through neural nets we have better contextual representations, not only of the words, but what the sequence of the words or even sequence of characters represent. And that has been shown to be extremely powerful. We have better sequence models. And so remember that named entity recognition task where we're looking for sequence of words that together define a medical term, for instance. Recurrent neural nets, either on words or on characters, are very exciting because they can capture rich long-distance dependencies in text, which was not possible with more different models like CRF, for example. Finally, there's really interesting work in learning models for mixed modalities. So what I mean by mixed modalities, things like text plus images, text plus laboratory tests, etc. And so, you know, we've had some example in the applications where we know that by incorporating all of this metadata, if you want, about a patient or about a individual online, we can actually predict better or understand better what this person is talking about or what a doctor is talking about with respect to a patient. And finally, there's interesting new type of machine learning. I'm thinking about adversarial neural nets and reinforcement learning in particular, where that are starting to show some very useful progress in NLP. So again, I'm not pointing you to any specific papers, but if you're interested, there are some classes online for you to look at. Okay, so I want to conclude by telling you that language is pervasive. It's hard to process automatically, and sometimes it's also hard for humans, but that's because there is ambiguity, there is variability and vagueness. But there's much progress that has been done. And I'll finish by saying that this is an active field of research, both in terms of the core NLP methods that are being developed, but also in ways of thinking of how to leverage text in general for biomedical knowledge discovery, characterizing diseases and behavior, improving care, etc. So with that, I'll stop, and hopefully there's enough time for questions.
Thank you, Dr. Elhadad, for a great talk and overview on NLP and sort of the medical and health domains. So we have one question for you from the audience. This first question is regarding privacy issues. And so you've been, a lot of the examples that you gave are from social media like Reddit and other areas where you might be mining forums and the such. Could you address how issues related to privacy and potentially de-identification are addressed in this type of work? Obviously that has applications also more specifically when you're mining clinical records, but if you could touch broadly upon that would be appreciated.
Great. Yes, that's a great question, and you're right, I didn't talk about this. So typically, you know, and I gave you an overview of like different papers out there, and everyone has a, you know, everyone has their own IRB of their own institution that usually makes sure that the methods are being, you know, respectful of the participants, in this case the people who write those texts or the people about which these texts are written. So when it comes to online health communities and social media, you know, most of the papers I've seen deal with publicly available, you know, data sets and text corpora. So for example, this breast cancer data set that I mentioned very early on is completely available online. Twitter is available if you don't pay attention to private messages, etc. There are some questions about how would you say you grow and crawl in the entirety of an online health community. How do you go about distributing this data? As researchers, we do not have the right to distribute it. We need to have, you know, somehow the agreement of the people who created and are monitoring this data. And so people have been looking a lot into how to de-identify texts. There are some both commercial and research de-identifiers out there. And it turns out it's a very institution-specific type of thing, where some institutions are okay with letting you distribute your data if you de-identified it, and others are not. There are de-identified clinical corpora out there. Mimic is one of them, and there are publicly available, you know, online health community out there.
Great. So our second question is actually about evaluation and what is the typical error rate in interpreting these texts as you apply natural language processing techniques. Obviously, it's not necessarily perfect, and as you pointed out, there's a lot of inherent vagueness to the text, so even humans are not necessarily perfect. But could you discuss what the typical error rate might be, and are there any examples where any misinterpretations have actually led to bad decisions?
Okay, so I feel like there's like kind of like two questions, like unintended consequences of recognition of something, and what is a typical error rate. It's hard to say what typical is. You know, if you think of a named entity recognition system, it's typically built with a terminology in mind for a particular type of text. And so if I take QMLS and CTEX and apply it to, or MetaMap or Medley, and apply it to an autism community, I might find that I have an error rate of say, you know, 40% in F measure. But if I were to do exactly the same and apply it to clinical notes, I would have an error rate of like 85 F measure. So it's difficult to say, you know, it's difficult to say out of the, you know, without thinking of the task, the corpus and the terminologies. For example, how accurate typically an entity recognition system is. And what this is pointing at is that there's not a whole lot of benchmarking in health NLP, but that's something that the community is working on heavily. So there have been for the past few years data sets that have been, de-identified in the case of clinical text, where gold standard annotations are provided for people to share, and there are challenges that let many different research groups try different methods, but everyone agrees to use the same evaluation metrics on the same benchmark annotations and text, and we can then compare, and understand which methods work better than another. I would say though that we're probably not as far ahead as we could be compared to other domains of NLP and other areas of machine learning, in part because of those privacy issues, for sure.
Great. So we're actually at 10 o'clock now, so being mindful of the time. Thank you again so much for giving this talk, and we'll close it here. Happy holidays, everyone. We'll be back in January 2017 with the next set of talks.
Thank you. Bye, everyone.